I'm Randy Seright, and I'd like to give you my thoughts on the important advances that have occurred that allow large-scale polymer flooding to be applied to the extent that they have as of 2023. And this is going to be a very quick summary of a recent paper that we published called Polymer Flooding: Current Status and Future Directions. And you can download this paper for free if you'd like from this particular website. For those of you who are not familiar with polymer flooding involves injection of viscous solutions of high molecular weight water-soluble polymers to more efficiently displace viscous oils from oil reservoirs. The first small trials of the polymer flooding process started about 1960, and the first truly large-scale polymer flood was begun in about 1996 and applied in the Daqing oil field in northeast China. Polymer flooding improves the reservoir sweep efficiency. So to illustrate this point, if we're injecting water to displace a viscous oil, it's going to take a lot of water before we really recover most of the oil that could be recovered by water injection. In other words, it's going to take many pore volumes of water injected before our oil recovery value goes particularly high. Now, alternatively, we can inject a much smaller amount of polymer solution and recover the same amount of oil. Polymer flooding also improves the vertical sweep efficiency in the sense that the oil that we are recovering is located in porous rock. And when Mother Nature lays down that rock, very often it's done in layers, so that some layers have a higher permeability or a greater flow capacity than others. And if we're injecting water to displace this viscous oil, that water is going to tend to finger or channel through the most permeable layer, or the layer with the highest flow capacity. And that means that oil will be more or less stranded in the other layers that have a lower flow capacity or permeability to them. By injecting this viscous polymer solution, we can substantially reduce that channeling through the most permeable layer and instead allow a much better sweep of all layers. So this is what we call improving the vertical sweep efficiency by injecting polymer solution. We could also improve the aerial sweep efficiency by injecting polymer solutions, in the sense that if we had neutrino ray vision and could look way down into the ground, and let's say we had a vertical injection well located here and a vertical production well located over here. And if we injected water to try to displace that viscous oil, the water is going to try to take the path of least resistance, and it will try to form fingers or channels as directly as it possibly can between the two wells. And of course, again, that's going to leave oil behind that might be stranded in various aerial locations. Well, if we inject a viscous polymer solution instead of water, that channeling process is much less likely to occur, and it's more likely that we will obtain a much better aerial sweep efficiency, a much smoother displacement of that oil. The polymer that's used most often for polymer flooding is called polyacrylamide, or partially hydrolyzed polyacrylamide, or very often we'll just abbreviate that as HPAM. And this is actually an acrylamide acrylate copolymer, which contains roughly on the order of 30% of these acrylate monomer groups and about 70% of these acrylamide groups. And these are strung together to make a long linear molecule, which typically is on the order of maybe about 20 million grams per mole molecular weight, which means it consists of a several 100,000 of these monomer groups stuck together. Now, this long linear molecule actually coils up on itself in solution, so it basically looks like a ball here. And all of the polymer molecules and chains that are entangled together, that's what gives the polymer solution its viscosity, because as you try to flow or move that polymer solution, basically you're trying to disentangle these chains, and that's what gives resistance to flow and your basic viscosity. So this HPAM, or partially hydrolyzed polyacrylamide, is the most commonly used polymer in polymer flooding, but we also have other polymers that are available to us. For example, one is called xanthan, which is a polysaccharide, and this polymer consists basically of a cellulose backbone, just a lot of sugar units stuck together, and that would normally be insoluble if it was cellulose, but this polymer also has these sugar side groups to it that make the polymer soluble. And rather than being a flexible coil, this particular polymer tends to form a double helix with itself and end up giving more of a semi-rigid rod type of structure. The nice thing about polymer solutions is that you can basically dial in any viscosity that you would like to see. So if I'm at very low polymer concentrations, maybe the polymer viscosity that you get out of your solution is roughly proportional to the polymer concentration of that solution. But once the viscosity rises above about 10 times the viscosity of water, for higher polymer concentrations, what you find is a nonlinear relationship between viscosity and polymer concentration, and that's a very beneficial thing because polymers are actually more efficient at viscosifying your solution at high concentrations than they are at low concentration. In particular, to a rough first approximation, when you get above 10 centipoise viscosity or 10 times the viscosity of water, then my viscosity of my solution is roughly proportional to the square of polymer concentration. So that means if I wanted to double my viscosity, I only need about 40% more polymer concentration to do that. And that helps us with respect to economics because obviously the polymer is by far the most expensive thing in a polymer flood. Okay, well that ends my very brief introduction to what polymer flooding is and how it's supposed to work. Now I'd like to move on for the rest of the talk and focus on why polymer flooding is being able to be applied on a fairly large scale now, a lot more than it ever has been in the past. And at the top of the reasons for why we can apply polymer flooding so effectively now is the fact that polyacrylamide prices, or HPAM prices, are actually lower now than they were in 1980. Remember I told you that HPAM, or partially hydrolyzed polyacrylamide, is by far the most common polymer used in polymer flooding. Now, it's interesting that polymer prices are so low since the consumer price index has increased by a factor of 4 since 1980. So we have to give much of the credit for keeping these polyacrylamide costs low to the polymer manufacturers and the advances that they have made in being able to make polyacrylamide cheaply. But we also need to give a substantial amount of credit to 3 large-scale polymer floods that have played a significant role in providing the market and promoting low-cost polymers, in particular low-cost polyacrylamides. Now this is really kind of interesting because back in 1986, most of the big oil companies really killed their efforts on polymer flooding and enhanced oil recovery type of projects. And their logic was that the cost of chemicals would always rise in direct proportion to the price of oil. And what we've obviously been able to see here is that simply did not turn out to be true, that technological and economic advances allowed the polymer to keep a low price, even though the price of oil has increased pretty significantly. Another very important thing that we've learned over the years is that if you want to have a successful, sustained polymer flood over a long period of time, you need to inject large banks of polymer. That is to say, a bank of polymer equivalent to at least 50% of the pore volume or the pore space in your reservoir. Now, when we're injecting the polymer, of course, the benefit we get is because that polymer is pushing from high permeability pathways down into lower permeability pathways, and in doing so, it's pushing a lot of oil back into the high permeability pathways and then onto our production well. But once we decide we're going to switch from polymer injection back to water injection, we now know that that water is going to form very severe viscous fingers or channels almost exclusively through the polymer bank in the most permeable pathway. That water is not going to be diverted down into less permeable pathways. Now, this is very much in contrast to the dominant view that was held back in the 1970s and 1980s. Back then, there was a common belief that we could inject a small bank of polymer, let's say maybe 5 to 20% pore volume bank of polymer, and the idea was that that polymer would dominantly penetrate into the most permeable pathway, and then when we injected water, that water would somehow slowly push that polymer bank intact through the high permeability pathway, and at the same time, water at the rear end of that polymer bank would be diverted down into less permeable pathways and would push out a lot of oil. And the problem is a lot of simulators would predict this kind of thing because simulations do not do a very good job of describing the viscous fingers or the channeling that occurs when that water really tries to just push its way exclusively through that high permeability bank. Now, we had to discover this mostly through experiments and through field applications. Simulations, like I say, generally speaking, gave us the wrong answer when it came to what was going to happen when water was displacing polymer solution. So the bottom line on this is once you switch from polymer injection to water injection, that water is going to break through the polymer bank in the most permeable pathway. Your water cuts are going to go very high, meaning your fraction of oil that you produce is going to go much lower. So if you want to have a sustained, successful, economically effective polymer bank over a long period of time, you need to be injecting at least a 50% pore volume bank of polymer. A property called injectivity is critically important to polymer flooding. Injectivity is basically how fast can you inject your polymer solution into the ground. The faster you can inject that polymer solution, the faster you can produce your oil. Now, if you have a vertical polymer injection well, one of the things that we now know is that you must have fractures that are open that intersect that well, because those fractures allow you to inject the polymer at an acceptable rate. Without them, you couldn't achieve an acceptable polymer injection rate in vertical polymer injection wells. And what happens with these fractures, if you're injecting just water, for example, maybe the fractures are very short or maybe are not even there. But as you inject something that's more and more viscous, or if you decide to inject faster and faster, or if you happen to inject dirty water, any of those possibilities, water that has a lot of suspended solids in it, is those things, higher viscosity, higher rate, or more particulates in your water, those things extend the fractures, make the fractures longer and longer to accommodate whatever rate or viscosity or degree of dirty water that you're accepting. That's what really happens with these fractures. As the fractures extend, it creates greater surface area, greater flow area for the water, the fluid, to penetrate into the porous rock. Now, of course, the concern with extending fractures is that if you have a vertical polymer injection well here and a vertical production well here, and that fracture happens to extend or grow all the way so that it connects up these two wells, then of course your injected polymer is going to just blast right through that fracture, and it's not going to be diverted out into the porous rock where it can displace oil. So in this particular case, that would have a very negative effect on sweep efficiency. But on the other hand, if I have a different orientation of my fracture, that's going to be potentially very beneficial. So let's say I have, again, a vertical polymer injection well here, a vertical production well here, and each of those wells is intersected by a fracture, and those fractures happen to be parallel to each other but perpendicular to the desired direction of flow. That's going to have both a very positive effect on polymer injectivity, because even if the fracture does extend more and more, it's not connecting the two wells, and it's also going to have an important positive effect on sweep efficiency, because basically these two parallel fractures are acting like two parallel horizontal wells and giving me a great sweep efficiency. Now, one thing that we've actually known since the 1950s is that even if I have a fracture that is pointed directly from the injection well towards the production well, that's not going to significantly harm my sweep efficiency so long as that fracture does not extend more than about 1/3 of the distance between the two wells. So the bottom line in all of this is before you start a polymer flood, it's really very important to know how fractures are going to grow, what direction they're going to go. And you want to place your wells to take advantage of that so that you get more of this type of situation where you've got a positive effect of those fractures, or those fractures have a positive effect on sweep efficiency, and not allow those fractures to cause direct channeling between the two wells. Now, fractures, open fractures in vertical polymer injection wells also play a very important role in mitigating what we call mechanical degradation or shear degradation. That's just basically breaking apart the polymer molecules so that they become lower molecular weight. Now, this diagram here is showing you the range of velocities that we would see in a vertical injection well if we had no fractures present, for example. So what we'd have is a vertical injection well, and we would have radial flow as the fluid penetrates deeper and deeper away from the wellbore into the formation. So very close to the wellbore, as the polymer just enters the porous rock, either through perforations or through open hole, the area open to flow with these two circumstances is very small. That means that the velocity of the polymer as it enters the porous rock is very high, and in fact it's so high that it will typically tear polyacrylamide molecules apart. Lower its molecular weight. By lowering its molecular weight, it's going to have a much lower viscosity after it penetrates radially and goes deeper and deeper into the formation. When the velocity slows down, what we'll find out is that the degraded polymer doesn't have anywhere near as much viscosity as we might have originally hoped. Okay. Now, there's another thing, is that the polyacrylamides that we use show what we call viscoelastic or shear thickening behavior in porous media. And what that means is that as I increase the velocity in the porous rock, my effective viscosity is going to be higher and higher. In fact, near the wellbore, it'll be so high that if I really didn't have any fractures, that would dramatically reduce the flow capacity of that well, the injectivity of that well, and it would basically mean I'm not going to be able to inject that polymer at an acceptable rate. So that would be two very negative effects, both degradation and a loss of injectivity. But fortunately, all of these vertical polymer injection wells have open fractures, and those open fractures radically reduce radically increase the area open to flow, and that radically reduces the velocity as the polymer enters the porous rock. And as a consequence, in all real vertical polymer injection wells, that they have fractures, and we really don't have to worry about this mechanical or shear degradation of the polymer, and we don't have to worry about this viscoelastic effect killing our injectivity here. And this has been controversial in the past because people have tried to figure out why our polymer injectivities in real vertical polymer injection wells has never really been all that much lower than in for water injectivity, and the reason is simply because these fractures are there. And this has been field demonstrated in the Mangala field, which is the second largest polymer flood in the world. That's located in India, and it's also been demonstrated in the Kalimkas field in Kazakhstan. And here's two papers you could download from the Society of Petroleum Engineers One Petro site. These are peer-approved papers that prove this point that I'm talking about here, that really all vertical polymer injection wells have an open fractures associated with them, and that has a very beneficial effect in mitigating mechanical degradation of the polymer and also aiding injectivity. So everything I've talked about so far, we've been discussing vertical polymer injection wells. For the last 20 years, we've found that horizontal polymer injection wells can be very beneficial for us in two ways. Number one, they certainly allow much less concern about injectivity because these very long horizontal wells have a lot of surface area associated with them, and so we have a lot less trouble getting the polymer into the ground than we might have with a vertical well, especially if you insisted that your vertical well didn't have any fractures on it. Now, another thing, and maybe even more important with the horizontal wells, is it has allowed us to extend polymer flooding so that we can now economically recover oils with viscosities that have a viscosity of 10,000 centipoise, that are 10,000 times more viscous than water. And the classic example of this is the Pelican Lake field in Alberta, Canada. This is the third largest polymer flood in the world, and this project has been very successful at recovering a lot of oil that we would not have recovered if we just allowed the polymer or the field to be produced by primary production or by injecting water. So this has been a very successful field and has been the inspiration for applying polymer floods in a number of other locations throughout the world, in particular at the Milne Point field on the North Slope of Alaska. Now, on the North Slope of Alaska, the Milne Point polymer flood, there's a number of pads or central locations where wells are drilled from, and here I'm talking about one of those pads called the J pad, which is a Department of Energy sponsored project that has just finished. And in this project, we had two parallel sets of east-west facing horizontal wells, two injection wells and two horizontal production wells, going after recovery of a 300 centipoise oil. So we're injecting basically a 45 centipoise polymer solution to displace a 300 centipoise oil. And this project has been very successful in the sense that there was a water flood applied before the polymer flood. Water injection occurred before polymer injection. And during that water injection time, the water cut or fraction increased up to about 70%. And in not too long, say about within a year of starting the polymer injection, the water cut decreased from 70% during the water flooding down to less than 10% during polymer flooding. And that's a greater reduction in water cut than any polymer flood that has ever been applied. So that demonstrates that polymer flooding can be extremely successful, especially when you're using parallel horizontal wells. So this is what we saw in the J-pad part of the Milne Point polymer flood. Turns out there are many other polymer flooding pads or locations where they're injecting polymer at this Milne Point North Slope project. Now, one of the things about the J-pad, which I just showed you in the last slide and is also reproduced here on the left side of this slide. Again, remember those are east-west facing horizontal wells. And one of the things we noticed is that the polymer broke through or arrived at the production wells after injecting 0.1 pore volumes of our polymer solution. Well, if everything worked the way the theory should, if the reservoir was homogeneous and fairly perfect, then really we would have expected the polymer not to arrive at the production wells until after injecting at least 50% of a pore volume of my polymer. Well, that raises the question then, why did the polymer break through after only injecting 0.1 pore volume of polymer? And a lot of us are convinced that the reason was because there is a north-south facing fracture or fracture-like feature, or maybe what they call up there a matrix bypass event that is allowing this injected polymer to go very directly between the two wells here. And to illustrate why that might be important, let's look at a different location called the L pad. And there, instead of having east-west facing horizontal wells, they have north-south facing horizontal wells. And in that case, even after injecting about 3/10 of a pore volume of polymer, there's been absolutely no breakthrough of water or polymer. And that's despite the fact that this polymer, or excuse me, this water is, the oil is 3 times more viscous in the L pad than it was in the J pad here. So what that's suggesting here is that if you have north-south facing fractures, if that's the direction that your fracture or fracture-like features want to grow, it's going to be best for you to drill your wells in a north-south direction, the same direction that those fractures want to go. And that's consistent with what I really talked about earlier. Different oil reservoirs have different temperatures, and if we're going to do a polymer flood, we need that polymer to be stable for the full length of time that the polymer is going to be pushing oil out of the reservoir, and that can very often be 5 years or more. So we need the polymer to be sufficiently stable and keep its viscosity for that period of time. Well, polyacrylamides, really we can only use them at temperatures up to from 60 to 70 degrees centigrade. Above that, they really aren't stable if the reservoir brine, the water that's in the reservoir, has any significant calcium or magnesium dissolved in it. And the vast majority of them do have a significant amount of calcium and magnesium. So that limits the use of polyacrylamides up to maybe about 60 or 70 degrees centigrade. Now, we do have other polymers that are significantly more expensive that could be used maybe in a little higher temperature reservoirs. And also, if the reservoir happened to have no calcium or magnesium at all in that particular reservoir brine, then we could make polymer or polyacrylamide work at temperatures up to around 100 to 105 degrees centigrade. But a really exciting development that has happened over just the past few years is that there is a relatively new ATBS-based polymer that is substantially more stable, and it could allow polymer flooding and other chemical-enhanced oil recovery projects to work at temperatures as high as 100 degrees or 120 degrees centigrade. So that is a big development that could substantially improve the potential for where we could apply polymer flooding. In polymer flood, it is usually critical to control the dissolved oxygen content. Now, this is very much in contrast to water floods. Often when you're just injecting water to displace the oil, the engineers maybe aren't really all that concerned about oxygen leaking into the system. That's because maybe it causes a little bit of corrosion and other problems. But in polymer flooding, it's far, far more important to keep your dissolved oxygen low. It's far more important than it is in a water flood. Any oxygen that leaks into the flow stream in a polymer flood is going to degrade the polymer and cost you lots of money and problems. I mean, I've seen cases where it could be costing on the order of tens of millions of dollars per year in just relatively small amounts of degradation that's taking place. So the rule that we have here is that if your reservoir temperature is below 50 degrees centigrade, then you should keep your dissolved oxygen in your water, in your flow stream, below 50 parts per billion. And if your reservoir temperature is above 50 degrees centigrade, it is absolutely critical to keep the dissolved oxygen as low as you can, ideally below less than 10 parts per billion. And a point here is that it really isn't all that difficult or expensive to maintain dissolved oxygen at very low levels. It just requires a very different way of thinking than we have in a water flood. And that's discussed in a lot more detail in the paper that I mentioned that's associated with this talk. If you inject polymer long enough, eventually that polymer is going to show up at your production wells. And of course, we want to separate the water from the oil that comes out of our production wells. And a lot of times we use what are called heater treaters or heat exchangers to facilitate that oil-water separation. Well, it turns out that the polyacrylamides we use in polymer flooding will hydrolyze at high temperatures. Remember, I showed you the structure of polyacrylamide a lot earlier, and that consists of a lot of acrylamide monomers and also acrylate monomers, typically about 30% acrylate monomers. But hydrolysis of polyacrylamides means that at high temperatures, those acrylamide groups hydrolyze to become acrylate groups. And if you get too many of those acrylate groups, let's say above 50% of the polymer becoming acrylate groups, then if there's any significant level of divalent cations in your water, like calcium or magnesium, that polymer is simply going to precipitate out of solution. And that's a big problem of why polyacrylamide is limited in stability. For long-term stability in our reservoir, we limit that to 60 or 70 degrees centigrade. But if we have a hot surface in our heat exchanger or heater treater, maybe 100 degrees or 150 degrees, whatever centigrade, then this fact is going to cause that polymer to hydrolyze very rapidly, and it'll precipitate, and that's going to plug up or foul your heat exchanger and cause big problems for you. So it can also cause problems in the rest of your surface facilities. So what that really means is that you need to, if you do start producing polyacrylamide, you need to keep the skin, the temperatures, the metal surface of your temperatures in your heat exchanger, you need to keep them at a reasonable temperature. And specifically for polyacrylamide, for the case at the Milne Point polymer flood, we found that temperature needs to be 120 degrees centigrade or below. Now, incidentally, if we use one of these newer polymers that incorporates this new monomer that I'm talking about called ATBS, that can improve the stability of the polymer. And incidentally, Chevron recently reported that they could move this skin separation temperature up to 160 degrees centigrade if that polymer contained at least 25% ATBS. So what I've talked about up to this point is giving you my views on those issues or those factors that have been most important to allow polymer flooding to be applied on a large scale as we have it today. But that doesn't mean there aren't a significant number of challenges that remain for us. And here I have a list of some of those challenges that still need a lot of work. And at the top of that list, I have the question of, does an aquifer or a gas cap compromise a polymer flood, or under what conditions does an aquifer or a gas cap compromise the polymer flood to an extensive amount? Another question which you'd think we'd have answered by now, but we don't, and that is, should a water flood be applied before a polymer flood, or how much of a water flood should be applied before a polymer flood, and how much good or bad does that do? A lot more work needs to be done on that. Another question is, can polymer reduce the capillary trapped residual oil saturation? Still, we have a lot of argument on that question. Should the polymer be graded at the end of injecting a polymer bank? Should the polymer concentration and viscosity be decreased gradually, or should we just go very abruptly from polymer injection to water injection? Understanding and minimizing polymer retention is very important to us. Polymer retention is basically how much of the polymer is adsorbed or mechanically entrapped, basically retained and stopped from flowing in the porous rock. We need to do a lot of work to understand that yet under different conditions. Can polymer flooding work in low permeability reservoirs? Virtually all large-scale polymer floods have been applied in very permeable reservoirs, that is to say, reservoirs that have an average permeability of 500 millidarcies or greater. There's a lot of interest in applying polymer floods, especially in the Middle East, in much less permeable carbonate reservoirs, and there's big questions about, can we propagate these very high molecular weight polymers economically and effectively through this low permeability rock? If we are producing polymer, can we produce that polymer and then recycle it, re-inject it, basically reduce the cost of the polymer simply because we're reusing it? Is that something we can do very effectively? And then finally, can a process where we have polymer injection alternating with either water or gas injection, could we make that work better than polymer flooding alone? Well, that takes us to the end of this presentation. Again, the whole goal here was to give you my thoughts on the important advances that have occurred to allow us to be where we are with respect to large-scale application of polymer flooding. And I do want to emphasize there's a lot more detail that is in this new paper that we came out with called Polymer Flooding, Current Status and Future Directions. You can get that really just by Googling it. There's a number of places you can get it, but if nothing else, you can get it, download it for free at this particular website. So thank you very much for listening.